Alright, in this tutorial we're going to do a nuts and bolts look at the four fundamental forces of nature. And then in class we will see how we can use those forces to explain certain particle reactions as well as other phenomena. We're going to get through about this page and half of the next page. I'm going to ask you to try to do some problems on your own. But it's pretty straightforward. There's a lot of little facts that you want to know, and we'll fill it out in a chart, but it hopefully is fairly straightforward. So before we get into the fundamental forces, we can look at fundamental actions that occur in nature, or interactions. And in English language, or in grammar, we call that verbs, right? There's a gazillion verbs that you could think of, like a push, a pull, a slap, a nudge, breathing, breaking apart, breaking up, crying, as shown above. Like matter, you can take every single action that occurs that's described by a verb, and even though there might be limitless numbers, you can reduce them to four basic interactions. And then what we want to see is those interactions are governed by four basic forces, coincidentally. So I want to start off by looking at the interactions. How does matter interact that gives rise to these verbs? All right, so the first two are somewhat familiar to us. They are attraction and repulsion. Okay, so it might not be obvious, but everything that I have listed up right here is either at some level an attraction or repulsion, or maybe a combination thereof. Okay, a push, you can think of, if I push against something, I'm repelling it, I'm pushing it away from me. There's a repulsion going on at some fundamental level. A pull would be kind of like an attraction. All right, so when you slide across a surface and you're sliding across the ground, we call it friction. You can think of that as either an attraction or repulsion. The key thing about that is that that's essentially 100% of your existence is either an attraction or repulsion. Okay, so while it might not be obvious why it is, what might grab you is, well, what on earth are the other two interactions that barely occur in our lives? Well, let me talk about those. They are at the nuclear level, and they are decays. And I don't mean like a decomposing apple or a dead hamster that decomposes when you bury it in the ground when you're a little kid. We're talking a decay like a radioactive decay, or decay of a muon, where it changes into another particle. And then the ultimate of that, and that's annihilation. Okay, we've talked about that in reference to creating energy from mass. So that's a very rare event, but it does happen. You cannot describe C or D as an attraction or repulsion. These only occur at nuclear scales. Right? But they're there. We want to understand them. Okay, so with that in mind, if we want to understand how those interactions occur, they need to be communicated by forces. Okay, and we can list a whole bunch of forces. We did last year. But it turns out those forces can be reduced to four fundamental, and that's what our focus is going to be on. Okay, so let's start with what we're most familiar with, and that's gravity. Okay, gravity is a fundamental force. So I'm going to move across, actually, let me talk a little bit here and there, and I'll fill this in as we go along. Okay, so two things we want to know about each of the forces is how far do they act and how strong are they relative to the other forces. All right, so gravity acts out to infinity. Okay, we kind of knew this already. I'm just going to divide this box up for the other part. So it reaches out to the farthest reaches of the universe, and it is always an attractive interaction. Okay, there is no repulsion amongst objects that are gravitationally affecting each other. All right, as opposed to another fundamental force that we talk about that is very important to us is the electromagnetic force. We used to think that electricity was separate from magnetism. The discovery by Oersted in the 1800s told us that they are indeed the same thing. Okay, so we lump it to electromagnetism. So everything that you learned that was about circuits or static electricity or magnetism are due to the same fundamental force. There are properties that are common to all those phenomena associated with it. All right, like gravity, the range of the EM force is out to infinity. Okay, unlike gravity, this is either attractive or repulsive. We've discussed this in great detail before, so we're not going to go through all those details again. Okay, so in terms of strength, I'll get to the strength part later. Okay, so what you might want to know about this, and we might talk about later, is electromagnetic force is essentially, let's say, 90% of your life. It is the basis for all of biology. And biology is really based on chemistry, and it's the basis for all of chemistry. To a certain extent, it's the basis for earth science, whereas gravity would be most closely associated with some parts of earth science and most definitely astronomy. So you can associate various forces with major courses of study. So what does that leave us? Well, the other two forces that we can talk about are not very common in our lives, and they are nuclear forces. So there is the strong nuclear force, and usually it's good enough just to call it strong, but I'm going to write nuclear. And then there is the weak nuclear force, which is the oddest of them. And we'll talk about them in turn, and I'll refer you to some links to maybe watch to give you a better idea of what they are. All right, what distinguishes the strong and the weak from the electromagnetic and gravity, and that why we don't see them in our lives, is because they act over very, very short distances. So I'm going to give you a scale rather than write short distances. We're talking nuclear, which is around 10 to the negative 15th meters or less. Okay, femtometers. Any distance beyond that, strong nuclear force is for all intents and purposes, 0. So if you're at atomic scales, an atom is roughly 10 to the negative 10th meters across, you're not going to feel the strong nuclear force across the entirety of the atom. Okay, it's only at the nuclear level, and the weak nuclear force is even smaller than that, but we'll just leave it as 10 to the negative 15th meters as well. I think it's closer to 10 to the negative 18th. But for all, let's put 18th then. Sorry about that. Okay, it is a exceedingly short range force that only lasts for a very brief period of time, and that it goes towards what it affects. Now let's talk about the strength, and I'll come back to that. So we can do these relative to one another. So the strong nuclear force is the strongest by far, and let's call it a strength of 1. Okay, so we'll build everything from there. The next strongest force is the electromagnetic, and it has a special number associated with it, but let's say it's roughly 1/100th that of the strong nuclear force. It's actually 1 over 137, but for all intents and purposes, pound for pound, the electromagnetic force is 100th the strength of the strong nuclear. The weak force is the next one. You might think it would be the weakest, but it's not, is roughly 10 to the negative 6th compared to that. So it's 1/1,000,000th the strength of the strong nuclear force. And the gravity, which has the most influence over the entire universe, is by far and away the weakest of all forces. It's roughly 10 to the negative 38 compared to the strong. Okay? I'm sorry, 10 to the negative 39. And we'll leave it at 38. Yeah, gravity just doesn't fit in. We still are trying to figure out how to fit gravity in at the very, very small realm because of that extreme weakness compared to the other ones. Okay? So you don't have to know these numbers. What you want to take away, strong nuclear is the strongest, gravity is the weakest, and the others fall somewhere between. Okay, so in terms of interactions with the strong nuclear force is by and large attractive. Okay, especially at greater distances. As the distance gets greater and greater, it becomes more and more attractive, like a spring, and then after some certain distance, it drops to 0. On the other hand, if you're at very, very, very close distances, it's actually repulsive. So it's kind of a weird force. But for all intents and purposes, let's just say it's an attractive force. Well, if you look at the type of interactions we've done so far, we've just talked about attraction and repulsion. So what's responsible for annihilations and decay? Well, you can probably guess. That's what the weak force is really about. So it dictates most decays. The strong does a little bit with decay, but heck, I'll throw that in there. Okay, and it also is responsible for annihilations. So what you can notice about the weak is that it does not hold things together. Okay, gravity, electromagnetic, and strong hold things together, just at different scales. The weak nuclear force does, if you will, just the opposite. It helps a particle become a different particle or to break apart in the case of a decay. So it's an odd force that way. All right, now, this is something we'll talk more about in class. If you want to understand how attraction or repulsion or other interactions occur, we used to talk about, especially with gravity and electromagnetism, as fields. There are fields that propagate out, and the fields interact with one another to attract or repel. It turns out a more sophisticated and ultimately more accurate way to explain all these is to say that what's really happening is there is an exchange of force carrier particles that we see or that manifests itself as one of those forces. And each force has its own distinct force carrier particle. Okay? These are not mass particles like leptons or protons, or quarks, with one exception. These are a different category called bosons. Okay, so the carrier particles have an important property. They're bosons, which we'll talk about later, whereas the mass particles are fermions. So let me give you what these carrier particles are, and then we'll talk about how they're affected, and that's probably as far as we'll get today. All right, let's start with electromagnetism. Electromagnetism, the force carrier particle is something we're very familiar with. It's called a photon. So a photon is a non-massive force carrier particle. When photons are exchanged between charged objects or moving charged objects, a force is felt. It's either attraction or repulsion. Those are our Coulomb forces or our Lorentz forces that are associated with magnetism. And what's really happening is when you exchange photons, you think of like a collision. If an object accepts a photon, it's going to kick back. And if I have two objects exchanging photons, they'll repel each other. Whereas if I have something grabbing a photon, it was kind of like an attraction. I'll explain that more in class. Okay? The strong nuclear force has two distinct carrier particles that do two different jobs. One is called the gluon. Okay? The gluon is also massless. It acts only over extremely short ranges. It's the glue that holds the nucleus together or holds hadrons together, something we'll talk about a little bit. But it's very distinct from a photon, but it is massless. The other force particle that goes along with the strong force are mesons. Mesons are bosonic. Okay, they act very, very different than the baryons that are also made up of quarks. So I'll talk more about that later. The weak nuclear force has three particles that are associated with it. One is called the W plus, the other is a W minus, and then there is the Z, which is neutral. And what distinguishes those bosons, the W plus, minus, and Z, is they're very massive. Okay? They are more massive than the top quark. So it's a very odd thing. And because they're supermassive, they cannot go very far. Their range is exceedingly small. And the last one that we want to talk about is gravity. And I'm going to put a question mark here because the force particle for gravity, the graviton, has not been discovered yet. Because it's so weak, we don't have anything sensitive enough to be able to measure them, but we're pretty sure that they are how gravity communicates between masses. All right, last thing I want to finish up with is what types of particles are affected by each of these forces. And this is something that's going to be important. So gravity affects every single type of particle. Okay? Anything with mass or energy can be affected gravitationally. If it's really tiny mass, it's extremely weak, but it's there. If you want to feel the electromagnetic force, you simply have to have charge. So any particle that we talk about that has charge, it could be a lepton, like a tau, or a quark, or an electron, or a proton, will feel the electromagnetic force. The strong nuclear force, on the other hand, only affects gluons. In other words, the force particles interact with themselves, which makes the strong nuclear very, very odd, and it only affects quarks, or hadronic materials. Okay, so what we notice it does not affect is leptons. The leptons do not respond to the strong nuclear force, and that has important implications. Whereas the weak nuclear force only works with quarks and leptons. Okay, so the electron is a lepton, will interact by the weak force. It will not interact by the strong nuclear force. It will interact